Hello everybody, welcome. Thank you for joining us today. You are part of the 500 people worldwide who have registered to view this webcast powered by Yole Development, System Plus Consulting, and Nomade, dedicated to VCSEL. My name is Faisal El-Kamasi. I'm Global Sales Support and Coordinator for Yole Development. Before we get started with the webcast, I would like to give you some information regarding the logistics. You have the possibility during all the webcasts to submit questions. In order to do so, you simply have to use the box at the bottom of the screen labeled Ask a Question. We will answer as many questions today as time permits, and for the remaining question, we will make a following up via email within a week. Concerning the material and contents, please note that the presentation is available and downloadable in the resource section. You will also receive an email after the webcast within 24 hours with a link to the recorded session. So today, Yole Development, Nomade, and System Plus Consulting will share their analysis for you on VCSEL. Let's start the webcast with an introduction held by Paras Mikish, Business Unit Manager of Solid State Lighting and Display Team. He is specialized in photonics, sensing, and display. Paras, please.
Thank you, Faisal. Thank you for this kind introduction. So good morning, good afternoon, everybody. Welcome to this webcast on VCSEL. So I will be your first speaker today. This is a session with 3 different presentations. So myself, I will focus on technology, industry, and market trends, whereas my colleague from System Plus and Nomade will much more, let's say, have some complementary insights from the reverse engineering costing and intellectual property perspective. So let's get started. So first of all, please keep in mind that vertical cavity surface emitting laser, that are commonly called VCSEL, is not a new technology. Datacom was the first industrial application to start integrating those devices in the early 1990s. Their sweet spot at that moment has been in short-distance data communication due to their low power consumption and the competitive price compared to edge-emitting lasers, also called EELs. And so those EELs are the second type of laser diode technology with VCSEL. Driven by the development of data center, the VCSEL market and production boomed in the early 2000s with the internet's popularity and then grew steadily. At that moment, some new applications for VCSELs emerged, like laser printers or optical mice, but were not strong market growth drivers. Not saying that they were not good business, but let's say that they were much more specialized or niche VCSEL application. It's only in 2014, so almost 20 years since the first use of the technology in Datacom, that VCSEL started to make their way into the high-volume consumer smartphone application. But this coupling with sensors for proximity sensing and autofocus functions was only the beginning of the VCSEL success story. Last year, Apple released the iPhone X with a 3D sensing function based on this technology. And this has made the VCSEL market explode in 2017. Such move from Apple has created a strong interest for this technology and is now likely to propel the VCSELs to a totally new market level. But before going into details of the 3D sensing application for smartphones and the related use of VCSEL, it might be worth getting an overview of the variety of applications targeted by VCSEL. So those applications are presented here. As you can see, they are mostly driven by 4 market segments: consumer, with applications such as laser printer, proximity sensors, autofocus system, facial recognition system, gas sensor, eye tracking system for AR, VR, gesture recognition system, computer mice, and so on. The second market segment is the automotive one, with the use in also the eye tracking system and gesture recognition system, but also technology or products such as LiDARs. Then we have the industrial one, so we have already discussed about Datacom, but there is also some products such as industrial heating systems that integrate VCSEL. Security and surveillance camera is also a good example here. And then we have the last one related to medical and healthcare, for which we have application in optical coherence tomography and pulse oximeters. So when we take a look at those market segments, so industrial applications were the first ones. Consumer applications are the ones that are currently booming, but automotive and medical healthcare applications are also of value as they represent potentially new relay of growth for VCSEL. We'll discuss on those applications later, but right now let's come back to the potential killer application of VCSEL, the 3D sensing one. So here on your screen, you have a slide that presents the true depth module of the iPhone 10 that was released in 2017. So for reminder, Apple, with this product, has opened the way to integration of VCSEL-based 3D sensing function into smartphones. Also, as an highlight, this technological choice of Apple has been renewed in 2018 and broadened to the whole range of iPhone presented last September. But the question is how and to which purpose does iPhone implement VCSEL? So if you take a look at the true depth module, you can see that there are subsystems, submodules. So the infrared camera, the front camera, the dot projector, the fluid illuminator, and the proximity sensor. So in red on your screen, you can see where VCSEL are being used. So you can also understand that 3 different VCSEL are being implemented into one, let's say, iPhone 10. So there are 3 units of VCSEL per iPhone 10. Please note that those VCSEL are different in terms of design, power output, chip surface, number of cavities, that there are different devices that are being used in the different sub-module, sub-assembly that you can see here. So for the proximity sensor, the device is much more basic than the one used for the flood illuminator or the dot projector. Here, I will stop myself here. If you want to have more details, we have made a webcast directly focusing on 3D sensing. I think it was in July, so you can refer to the archive section of iMicronews in order to see this replay, and in which you will have further highlights on this true depth module analysis. And the webcast was done by my colleague, Pierre Cambou, who is our, let's say, a senior analyst specialized in imaging. So now if we come back to, let's say, the global trend related to iPhone, the fact is that the iPhone 10, the sales related to the iPhone 10 was really good, and this has triggered the interest of other smartphone brands in this breakthrough 3D sensing function. And less than 1 year after the release of Apple's flagship, several competitors have followed the same trend and started to integrate this 3D sensing technology. Xiaomi and Oppo were the quickest on the draw with the Xiaomi Mi 8 Explorer editions and the Oppo Findings models that were presented in the second quarter of 2018. Vivo then in June also presented its 3D sensing technology, and more recently Huawei unveiled its P20 Pro integrating such function. I think it was, let's say, 2 weeks ago, 2 weeks ago. So the question is, will Samsung be the next player? So several rumors point out that company's Iris scanner, which is based on LED infrared, LED, if this Iris/face scanner technology will be replaced by a 3D sensing camera on the next year's S10 lineup. So today, there are several rumors, but this has to be confirmed yet. Here, please note that most of the, let's say, different reference that I have mentioned, reference of smartphone that I have mentioned integrating VCSEL, will be presented or, let's say, much more investigated during the presentation of Romain Fro from System Plus Consulting, so at the end of this session today. And you will have much more, I would say, reverse engineering, reverse costing analysis related to some of those smartphones here. So let's continue now our presentation to try rapidly also understanding the use of 3D sensing in a smartphone's front camera. So biometry is currently the major driving application. So whether it is to unlock the phone, but also for the mobile payments that are getting more and more popular all around the world. But in the future, 3D sensing will act more and more as a new mobile user interface for application on social platforms such as the virtual chat rooms and so on. So we are really at the start of, let's say, a 3D sensing application into smartphone products. So in this context, in this booming context, I would say, the explosion of VCSEL demand initiated in 2017 is likely to persist for the next 5 years and potentially multiplying the business opportunity by a factor of more than 10. So we have estimated the market size at the device level, so chip, VCSEL chip on submount or VCSEL package, I would say, of $330 million in 2017. This market is likely to reach a size of $3.5 billion in 2023. During that time, the technology might also find some new growth drivers into some other volume applications, such as automotive LiDARs, but also gas sensors, OCT, optical coherence tomography, or additive manufacturing. Some of those applications could act as a major growth driver for VCSEL business at middle and long term. In this field, LiDAR might represent a good prospect. However, the use of VCSEL is still under question as most of LiDAR companies implement edge-emitting laser in their products. Today's concept of semi-autonomous cars mostly implement centralized LiDAR, meaning one or let's say some few LiDARs, but at the central level. But for fully autonomous cars, they might implement also some local LiDARs requiring lower distance detection range and for which VCSEL could provide some advantage towards EES. So now that we have seen market perspective, let's take a look at the industry aspects. Here, one of the key messages to highlight is that the new wave of investment and merger and acquisition has already started and different strategies are being put in place. There are some moves to diversify activities and rapidly enter the VCSEL business, such as Ultram, who recently acquired VCSAR. There are some moves to get vertically integrated, such as II-VI, who acquired EpiWorks, or AMS, who acquired Princeton Optronics. There have been some investment to increase the VCSEL manufacturing capacity or to develop the 3D sensing VCSEL supply chain. Here, a good example is the investment of Apple in Finisar to develop a secondary supply source. So honestly, I don't know if we can consider that as an investment or an award, but the objective is the same for Apple. They don't want to be dependent only on Lumentum, who is the, let's say, sole and main provider of VCSEL for Apple regarding its iPhone production. And so the objective is really to have, let's say, a secondary source for Apple. So in addition to investment or merger and acquisition, another trend in the VCSEL industry is related to the entry of new players, and those players want to benefit from the booming 3D sensing opportunities. They are mostly coming from the depressed LED industry that still suffers from overcapacity and strong price pressure environment. Those LED players are also familiar with the manufacturing of gallium arsenide-based optoelectronic devices, which, let's say, offer them an advantage. However, we expect several of them to fail being qualified and entering this 3D sensing VCSEL business, as the technological roadblocks are quite high, difficult to lever. Indeed, when taking a look at the VCSEL supply chain for 3D sensing, it is important to understand that there is no real vertically integrated players as of today. There are mostly specialized players at each level of the supply chain, whether it is related to epitaxy, to the front end or the packaging. So this is really highlighting how VCSEL devices are difficult to manufacture today. And the main, let's say, challenge I would say, or I will summarize all the different challenges as the one regarding the yield and the cost aspect. As mentioned earlier, the devices that are being, let's say, produced for datacom and 3D sensing are totally different. The design are different, the targets in terms of cost are different. We could summarize, let's say, this move from datacom to 3D sensing as a move from 4-inch manufacturing to 6-inch manufacturing. We for sure increase the design aspects and so on, but this move from 4-inch to 6-inch manufacturing is really representative of the difficulty today of entering the 3D sensing supply chain at the device level, because the yields are really low, and when I say yield, it's mostly the run-to-run repeatability, and there is a real lack of, let's say, tools and equipment or knowledge, I would say, to be able to monitor the device manufacturing, whether it is related to the growth of epi layers or, let's say, the etching of the cavity and so on. This is, let's say, sorry, I forgot this slide. So this one is related to what I have tried to explain you since, let's say, the beginning of this presentation, that not all VCSEL devices are equal, and that the design of the VCSEL device will be dependent on the application. So here you have an example of some VCSEL that are being used for datacom and proximity sensors on the top. On the second line, the one that are used for gesture recognition. On the third line, the one that are used for 3D sensing. And on the last line, an example of, let's say, design for LiDAR. You can see that the die size are different, the number of cavities are different, the power output are different. So if you want to target a specific application, you will need also a specific expertise in order to manufacture the, let's say, the VCSEL that is in agreement with this application. And here to, let's say, finish on my presentation and related to a manufacturing challenge, the idea of this slide was mostly to summarize, let's say, the front-end manufacturing challenge. So we have discussed about the epitaxy growth and the need to control, let's say, this epitaxy growth in order to have higher yield, which will allow to, let's say, have also lower cost. There is also, let's say, some challenge related to the mesa etching aspect and to the control of the oxidation rate and speed. So now I have finished with my presentation. I will let now VCSEL introduce the next speaker, Paul Leclerc from Nomade.
Thank you very much, Paul, for this nice presentation. Just to remind you once again, do not hesitate to ask questions using the Q&A button for the Q&A session at the end of the webcast. So let's continue with patent landscape analysis from Paul Leclerc, patent and technology analyst at Nomade. Paul, the floor is yours.
Thank you. So yeah, I'm Paul Leclerc, and the following part is related to the patent and IP landscape analysis of the VCSEL. So in this session, I would like to give you an overview of how the IP landscape deal with this VCSEL mutation of the market, and how it is impacted by all these new applications that are rising from the consumer market. So to start with the IP landscape related to VCSEL, so as Par said, VCSEL is not a very new technology, and for IP landscape point of view, it's also very old technology, because the first patent publication that we identified that have been related to VCSEL were published in the 90s, and all of these VCSEL-related patents were related to datacom and telecommunication application. And so for a long time, datacom was very the driver of the IP activity. And in 2000, another application have also rise, which are the laser printing application. And in fact, these two main applications were really the main driver of the IP activity for almost 2 decades, and they really drive the IP activity related to VCSEL. And in fact, we reached a plateau between 2002 and 2007, and most of the time when we reach a plateau in the IP landscape, it means that the IP landscape is mature, the technology is mature, and so you have very strong IP leaders, and it's more about keeping your IP updated and giving some new invention, but all the work, all the development are already been done in the past. And this plateau keep continuing today. And as you can see, even for the last 3 or 4 years, we haven't seen any very huge increase of the patenting activity related to VCSEL. And that's something very interesting, because as Par said in this presentation, we expect from the market that many things will happen for the VCSEL, but nothing can be seen from the IP dynamics, and that's something that is very strange, and that's also something that I want to answer today, is why can't we see anything from the IP point of view, but we expect a lot of things from the market point of view. And in fact, to answer this question, we have to go a little bit further in the analysis and to look at what kind of application are mentioned in the patent. So as you can see on the graph on the left, datacom or laser printing are by far the main application that have been mentioned in the patent related to VCSEL. And since 2007, 2008, you can see that there is a small decrease of the patenting activity related to these two applications. And so that's explaining why we saw a small decrease in that time and the overall IP dynamic. But on the other hand, you have 4 new applications that have become more and more mentioned in the patent, which are atomic clocks, medical imaging, automotive sensors, especially LiDAR, and consumer sensor with 3D sensing application. And in fact, these 4 applications show a very high growth rate regarding the IP landscape, because you can see about 10% growth rate for atomic clocks and even 45% for a consumer application, which is very high. And so, in fact, if we want to understand the current trend and the current really high dynamic around VCSEL, we have to look in these 4 new IP domains, which are very, let's say, little compared to the datacom and the laser printing application. So really, if we want to understand what are the new driver and what are the challenge and what are the inventions that are really important for the IP point of view, we have to look into this implication and to understand who are the players that are now driving the VCSEL development and what technology are they looking into. And so this is what I'm going to do in the next couple of slides. So if we look, first of all, at the less dynamic or the less interesting market because of their market value, which are the atomic clock and the medical imaging part. In fact, here it's very obvious and very interesting at the same time, is that when you look at the 4 main IP players related to laser printing, so Ricoh, Canon, Epson, and Fuji Xerox, you can see that all of them but Fuji Xerox are progressively switched from their main application, which is laser printing, toward new application. So for Ricoh and Epson, they have started to patent several applications related to atomic clock application, and for Canon, they have started to look into medical imaging application and especially OCT. So in fact, the growth that we see in the previous slide regarding the IP activity related to atomic clock and medical imaging is the result of the activity of these 3 main IP players that come from the laser printing application on the laser printing market. So for these 2 applications, it's really matters of main IP players that are really going from one activity to another and to other application. But now if we want to understand what is happening to the killer application, so the 3D sensing, we have to look at different aspects, and that's a little bit more tricky to understand. Because first of all, if we look at the 3D sensing, the first player that I've mentioned 3D sensing are players from the datacom. So you have Finisar, which is well known and have communicated about its VCSEL for 3D sensing, but you have also Avago Technologies that have started to mention 3D sensing in their patent, and also Sony. And what is interesting here is that these 3 main IP players from the datacom segment are not focusing their IP activity on 3D sensing. They are just starting to mention some invention that could be used in 3D sensing, but their main priority and their main focus is still datacom. So it's a small shift. Maybe they probably will keep filing patents related to 3D sensing, but up to now their patent portfolio is very poor or very weak regarding this new and trending application. The other players that are now looking into this application are, let's say, more specialized players and players that are mainly known from the market point of view. So in the IP landscape, we have identified 5 main players, which are Philips, Lumentum, so 2 providers of Apple, Osram, AMS Group, that's just acquired, so Heptagon and Pryston, and Trilumina. And here what is interesting is that for Philips, Lumentum, and Osram, 3D sensing is not their main or their first application that they were protecting or they were addressing with their VCSEL portfolio. In fact, they are all started with either datacom or even other applications as industrial application. But the rise of 3D sensing offer a new opportunity for this IP player to enter a new segment and to really lead this segment by providing a lot of patents and to try to really strengthen their position regarding this segment that is very promising. So this player, even if they have a young portfolio and relatively weak portfolio, they are the players that are really specialized into this segment. And finally, they also have many newcomers that have entered the IP landscape related to VCSEL. And that's something also very interesting because we have identified more than 50 IP newcomers since 2010 that have started an IP activity to mention or to claim VCSEL in their patent. And as you can see on the list, there are some very big names here, and it could mean that more and more development and more people will look into VCSEL. For example, you have Murata Manufacturing that have filed a couple of very interesting patents related to the VCSEL manufacturing. You have Stanley Electrics that also holds several very interesting patents related to VCSEL array manufacturing. So there is a lot of new IP comers and that are providing very interesting invention and very interesting portfolio. And also what is very interesting here is that these newcomers are entering the 3D sensing or LiDAR segments. And so it's not providing VCSEL for any kind of application. They really mention this specific application because it shows how these applications are attractive and they want a part of the big cake. So if I have to sum up my talk, in fact, we are really witnessing a change or a mutation of the IP landscape, and we have 2 main IP strategies that emerge. You have a first strategy that is the main IP player that come from other markets, especially datacom and laser printing, that are trying to enlarge their IP portfolio by addressing new application. So for the laser printing players, they address small or medium-sized markets that are medical imaging or atomic clock. And for the datacom, they are more looking into the consumer application. On the other end, you have a very specialized player, so Philips, Osram, or Lumentum, that are decided to directly enter the IP landscape related to consumer sensing application. But because it's a young and application, their portfolio are still weak and need to be developed and strengthened. And then you have sort of confrontation between the old and very strong IP player from the other segments, segment of application, and these young specialized IP player that need to strengthen their position. And these 2 worlds will confront, and so we expect a lot of new M&A, a lot of litigation because players are also very aggressive. For example, Philips or Apple are well known for attacking their for patent infringement. So we expect a lot of new litigation coming up, and also something that will probably happen in order to increase the development and the entrance of players into this market is IP collaboration, because as Par said, there is there's a lot of difference between providing a VCSEL for datacom and providing a VCSEL for consumer application. And so if you want to increase and to make your way into this new market, IP collaboration could be a good way to make your progression faster into that market. And finally, I just want to highlight a specific thing related to VCSEL is that even if for example, Philips or Lumentum, so the specialized player, have a small portfolio, their portfolio is really dedicated to strengthening their market position, because as you can see on this slide, which is a summary, or let's say a small part of our patent to product mapping that we've done in July of this year, you can see that Lumentum or Philips are already filing patents. They are not granted yet, but filing patents that are directly related to their VCSELs that are in the iPhone 10 product. So I will let Romain explain about some of these features, but they have the IP and they have the capacity to now block their main competitors and to really assert their market position thanks to their IP portfolio. So if I sum up my talk, I would just say that the IP analysis attests of a strong mutation of the VCSEL landscape, where in fact old and historical applications of datacom and laser printing are less and less mentioned in the patent, and new application, and especially 3D sensing and LiDAR, are becoming the new driver of the patenting activity related to VCSEL. And also what is very interesting today is the 3D sensing IP landscape is very young and unsettled. But as Paul said also, it's very interesting because the market value is very high and the growth rate is very high. And so most of the players are now willing to be part of this segment and also willing to assert their position. And so because of that, we expect a lot of litigation on M&A that will happen in the next couple of years. Thank you for that attention, Faisal. I'll let you the floor.
Thank you very much, Paul. Great presentation also. Thank you very much. Let's do now the last presentation of the day. So we have Romain Fro, CEO of System Plus Consulting, who will now provide a technology overview of VCSEL. Please, Romain.
Thank you very much, Faisal, for this very nice transition. I'm happy to be here today to present some slides coming from a report we publish on 3D sensing devices. So we just had a very nice presentation from the market point of view, technology, and patents. So I'm happy to conclude with some example of consumer 3D sensing product showing how they are constructed and what is the content in terms of VCSEL. So I will start with some supply chain which are estimated by Yole here. It's quite interesting to see that the market is really complex in terms of supply chain. So we have here an example of 3D satellite cameras supply chain. So from system OEM like Apple, Huawei, Xiaomi, Oppo, and maybe Samsung in the future. So it's not an easy task to be able to assess the supply chain. As you can see, there are a lot of different companies which provide different elements on these systems. So there are few providers of architectural wafers, but there is right now some player providing VCSELs. We know that it's not easy in terms of manufacturing, in terms of yield. So there are few companies which are able to produce enough volume to support the smartphone 3D face recognition activity. And we will see in the next slide from examples that most of the players are integrated in the same smartphones. I will not cover the other parts of the 3D camera, which are the sensors and the camera modules, and here I will focus much more on the VCSEL part. So for sure, as Bart mentioned, the first, we'll say, killer app has been Apple with the iPhone 10 and the Face ID face recognition system. It's really interesting, so as already mentioned, that a lot of VCSEL are used here in order to be able to provide the dot projector, the fluid illuminator, and there is also one small VCSEL in the proximity sensor. So Apple is using a structured light approach, but also linked to the fluid illuminator and proximity sensor. There is also a time of flight which is used in this phone. So if we go a little bit more in deep in the true depth module, which is used for the face recognition, we have here a very compact module. So it's also really interesting in terms of integration because it's really complex to integrate as many sensors in this small space. So we can see that at least 4 or 5 sensors are used with an infrared camera sensors, proximity and fluid illuminators, a dot projectors, and also an ambient light sensor. There is different providers, different players which are entering in this supply chain. From what we observed by analyzing several iPhones, in terms of VCSEL, Lumentum is providing the chips. We can be sure that maybe Apple would like to secure with other suppliers, but right now it seems that Lumentum is one of the only players able to supply with such a large volume for iPhone. So the dot projector used by Apple in the iPhone 10 is made by mostly by AMS using Lumentum VCSEL, and as you can see on the picture, it's quite an impressive module which uses a VCSEL for sure for the emitting part, but also other kind of silicon content with drivers and so on. So in terms of integration, it's quite complex, and also the VCSEL needs some specific integration with specific substrate in order to be well integrated in the system. So if we now have a look at on the die, the VCSEL die, which are used by Apple in the dot projector and the fluid illuminator, we can see here that there is 2 different VCSEL. So I will not cover the VCSEL for the proximity sensor because it's not very new. It has been used by other players for proximity sensing in the past. But the VCSEL for the fluid illuminator here, it's 0.5 square millimeter die size with 120 cavities. And if we compare with the VCSEL dies which is used for the dot projector, also provided by Lumentum, we can see that here the die size it's twice the size with a little bit more than 1.1 square millimeter and with a little bit more than 320 cavities. So it's really interesting also to have a look at the process level. So you have an example of a cross-section here of the VCSEL from Lumentum, showing the epitaxial layer, the substrate, and also the cavity. So here the epitaxial layer are not easy, not very easy to sew, but there is a very, very complex structure which are quite similar to what we can find in a LED product, and it's here that we can see that the complexity is really key. And in terms of manufacturing process, manufacturing cost, it's something which is quite important right now. So I'm sure we'll come back on the yield, but it's also a very big impact at the end in terms of manufacturing cost. So we made some cost calculation of the true depth module. So here you have a breakdown, a cost breakdown of the module, so without the RGB camera. And we can see that the cost has been estimated to be around $14. And a big part of this cost is linked to the dot projector with more than half of the cost, and also to the fluid illuminator and the infrared sensor. VCSELs here are really important in terms of share. So we have 30% of the cost of the complete module, which are estimated to be linked to the VCSEL dies, which is really, really important in terms of manufacturing cost at the end. Now, if we have a look on the other smartphones which are provided with face recognition, 3D face recognition. So as Bart mentioned, Oppo, Xiaomi, and Huawei also followed the Apple introduction. So this year, end of the year. So the Oppo Find 10 here use also a structured light approach. The dot projector, in terms of resolution, it's half compared to the one of iPhone of the iPhone 10. So it's only 15,000 dots, which are used for the resolution. In terms of structure, now we can see that it is quite similar. The main difference is the integration approach, which is, I would say, less integrated compared to Apple, but it's still the same kind of sensor which are used with a dot projector, a fluid illuminator, an infrared camera, also an ambient light sensor, and a proximity sensor. The main difference compared to the TrueDepth module from the iPhone is that the fluid illuminator here do not use a VCSEL, so there is only one VCSEL used for the dot projector. The fluid illuminator here only use an infrared LED, which is really similar to the kind of LED used for iris scanning. So what we can see from this solution, which has been developed by Orbeck, is that the dot projector module is really, really different compared to the dot projector used in the iPhone 10. The structure here looks like a camera module with plastic lenses, which is really different from the AMS approach using wafer level optics. In terms of VCSEL, it's quite similar in this case because it's also Lumentum which is providing the VCSEL. The die size is half the size of the one of the iPhone 10, 0.6 square millimeter, and also the cavity number is less important with 180 cavities used by this VCSEL. Let's continue with another smartphone OEM, Xiaomi. Also, they introduced a new flagship with Xiaomi Mi 8. So it was quite interesting to see here that they released two versions. So the Xiaomi Mi 8 standard version is only using an infrared face unlock, so no VCSEL. Infrared is used with infrared LED. And on the other hand, they also released a more high-end version of the Mi 8, which is the Explorer edition, which uses a 3D face recognition. It's really difficult to obtain this phone. It seems that the volume is not really huge, so nothing compared to the iPhone and also to the Oppo Find 10. If we have a look now at the module, it's also quite interesting because they are using a quite compact module, using also two VCSELs in this structured light technology approach. The resolution of the dot projector is really similar to the one which is provided by Apple with 33,000 dots. And also, what is quite interesting here is that they are using the same VCSEL dies for the fluid illuminator and the dot projector. So right now we are just investigating this VCSEL. According to Yole, the supplier could be Finisar, but it's something we will dig a little bit more before being sure of the supplier. So we have a very large VCSEL in this case, 2 square millimeter. So it's almost twice the size of the VCSEL in the iPhone 10, and also the number of cavities is quite impressive with 977 cavities. The pattern is different. It's not a random pattern in this case, so it's also something which is important to take into account in this case. So just to conclude on the mobile camera, also there is not only structured light. Also, and I'm sorry here, the title is not the case. It's not the supply chain for structured light camera, but for time of flight camera. It's another approach which is also used by other players. And this technology also needs some VCSEL for illumination. So in terms of supply chain, as you can see here, other providers, other OEM are following this time-of-flight approach. So Lenovo and Asus has been the first, in fact, to integrate 3D sensing on the rear side of the smartphone. So Lenovo was the first with the Google Tango project, using an Infineon PMD solution for the sensor and a VCSEL for the emission. So if we have a look at a little bit more closer at the structure, we can see that the supplier of the VCSEL at the time was Preston Optronics. And we have quite a small VCSEL, 0.6 square millimeter, with 200 cavities, which is something which has been improved also now by PMD and Infineon, because they are now proposing a more compact module and with different approach and different technologies also. Finally, VCSEL are not used only in smartphones, as Pars and Paul mentioned in their speech. We also observed some different VCSEL, so same technology but different size. In this example of a product proposed by Intel, which is a RealSense technology. So it's depth camera which are using stereo vision in this case. So as you can see on this product, they are proposing some module with two CMOS image sensor provided by OmniVision, and a projector which is a VCSEL provided also by Princeton Optronics. So if we have a look a little bit closer at the VCSEL, it's really interesting to see the difference compared to the one which are used for 3D face recognition. In this case, we have a very large VCSEL die, close to 5 square millimeter. So if we compare this to the 0.5 square millimeter of the iPhone, or even if we compare with VCSEL from proximity sensor, which are much lower compared to 0.5 square millimeter, here we have a very large number of cavities. So it's more than 6,000 cavities for this VCSEL. So for sure, in terms of integration, in terms of process and cost, it's more complicated. And at the end, it's a solution which is really difficult to be integrated in a smartphone linked to this cost aspect. So we also made a cost estimation of this module. So there is here a complete electronic board to take into account with sensors, with other kind of components, and with optics. What we can observe from this cost estimation is that we have a module which is in the range of $30, which is also quite expensive compared to smartphone solutions. And the most expensive part of this board is also the VCSEL. So we calculated that 30% of this cost is to be attributed to the VCSEL linked to the large size, and with the yields we have right now on the market linked to this complexity of manufacturing, we understand quite easily that there is a lot of possibility in the future for reduction at this level. So thank you very much for your attention, and I will let Faisal conclude on this very nice webcast.
Thank you very much, Romain. Great presentation also. Thank you, all of you. Now we have about 10 minutes, so we are going to wrap up with a Q&A session. We will answer as many questions as we can, as we have about 10 minutes for that. And for the other question, we will do a following up via email. All right, so some question, we receive a lot of questions. I guess, Pars, we'll start with you. According to you, so who are currently the top VCSEL device players?
Thank you, Faisal, for this question. So yes, this is a really interesting question. Today there are, let's say, 5 top players within the VCSEL industry, within the VCSEL device industry. Those players are Lumentum, Philips Photonics, II-VI, Finisar, and Princeton Optronics. I would say that before 2017, they were in the, let's say, same range of market share, let's say in the 10 to 15% market share. But with the release of the last iPhone, one supplier has been favored in terms of volume and revenue, and this is Lumentum. So today the top player is Lumentum with a much more higher market share compared to the other players. But those are the top five, and they account for nearly, let's say, a little bit more than 60% of the VCSEL business today. But once again, the industry is under, let's say, mutation. So this picture is the one for 2017. Let's keep an eye on what is likely to happen in the coming years.
Okay, thank you, Paul. I think, Paul, this one is for you. You mentioned some M&A. So in your opinion, what would be the next M&A and who would benefit from it?
Interesting question. M&A, in fact, M&A up to now, M&A were done by most of all sensing players that wanted to develop their product and to start to enter the proximity sensor or the 3D sensing and needed to bring a new expertise regarding VCSEL. So, for example, you have Osram that have, with the acquisition of VCSEL, have really developed its portfolio and now came with a product. I think one of the best moves has been done by AMS. We didn't have any IP, so probably not much of expertise in VCSEL, and just by acquiring Heptagon and especially Princeton, they really get a very high IP and know-how, and they can they now have an interesting position regarding the IP landscape. If we look at the upcoming M&A, what is interesting up to now is that the newcomers and the players that have a very interesting IP to acquire are already big groups. I mentioned Murata, I mentioned Stanley. They are recent, so they could be interesting to acquire, but it's quite difficult to acquire Murata or acquire Stanley. So maybe the best targets are the specialized players that are young and that can that already have a foot in the consumer sensing application, and they can really use their know-how and their IP to really evolve with the help of someone else. So I think the M&A will probably happen with people that are specialized in the VCSEL for 3D sensing especially, but not from newcomers that are now, most of them are really big groups that are difficult to acquire.
Okay, thank you, Paul. Roman, a question for you. Are there new features in the last phase ID modules of the iPhone XS and the iPhone XR?
So thanks for the question. It's so we already opened some of the new version of the iPhone. So it's true that we are still using a picture coming from iPhone 10. So it's a little bit more than 1 year ago. So what we observe is that in the latest iPhone XS, iPhone XS and XR, they are using the exact same 2D module. I'm sure they invested a lot, and then it's the same module, the same component from what we saw, so same VCSEL also. So it's really difficult for Apple products to be sure that they do not use the dual source, for example. But from what we saw right now, iPhone XS and XR are using the exact same hardware in terms of the module, the 3D module, compared to the iPhone 10.
Okay, thank you, Roman. Parth, can you give us more insight on yield aspects
Yeah, sure. So yield is really one of the major problematic, I would say, to enter the VCSEL business for 3D sensing again. Making VCSEL for datacom is totally different than making VCSEL for 3D sensing. And so as I mentioned in my presentation, so when you move to 3D sensing, there is a transition to the 6-inch manufacturing. And here today, the yield are really low at epitaxy, at chip manufacturing level. Typically, we'll try to give you some figures in order that you could have a vision about, let's say, the yield that we have estimated on the last iPhone. Just one second. So in 2017, we were, let's say, estimating a manufacturing yield. So from the raw substrate, the gallium arsenide that is being used in order to make the epitaxy to the final chip of between, I would say, 10 and 30% for the VCSEL used in the dot projector and the fluid eliminator. For the VCSEL used in the proximity sensor, the yield are slightly, let's say, higher, better, I would say, because those proximity sensing VCSEL are more easier in terms of design, more, let's say, require lower use of lower performance. But the yield is really the problematic. Here I give you some figures related to the chip manufacturing, but if you take the line yield, the global yield, so typically how many chips are produced and how many of those chips end up in a smartphone. Today, just to give you some raw figures, I think this yield is in the range of 10 to 25% maximum. So it really shows you how this problematic related to yield is important in this emerging VCSEL industry for 3D sensing.
Okay, thank you, Paul. Maybe another question in carry on to this yield. So Paul, maybe for you, how players address the yield improvement challenge in their patents, and is there any noticeable development?
Yeah, in fact, yield is a very wide topic. And as Parth mentioned in his talk, you have several aspects. You have the yield coming from the epitaxy. You have also the yield coming from the manufacturing. And it's totally different whether you are looking for answering yield from the epitaxy part or yield for the manufacturing part. Regarding the IP, let's say most of the solutions are really related to how to improve the yield for the manufacturing part, because as I mentioned, VCSEL is an old IP domain, and many things regarding the structure and regarding the EP of the Bragg reflector on the active region have been done by players from the datacom, even if it's another application. And their patents are already quite blocking. They block the publication of new patents. So there is not a lot of things that happen on the epitaxy side. On the manufacturing side, however, most of the players are looking to especially address the oxidation step and how to enhance the oxidation. So I would say that the yield in the patent are really related to how to enhance the manufacturing step, and especially all related to either oxidation step or meso etching step.
Okay, thank you, Paul. We might have just a last question, Roman. Do you expect, maybe quickly, do you expect cost reduction in the next few years?
Okay, I will be quick. Thanks, Faisal. I think the question is really linked to the previous question also, because on our point of view, in terms of cost, for sure, if the yield can be improved, the cost will be quite reduced. And for sure, there is also a way to reduce the cost, but right now, the yield, in our point of view, is the major factor of cost, and by improving the yield, for sure, the cost will be really improved. After that, wafer size increase and other kind of dicing process could increase the cost, but the yield, in my point of view, it's around right now the major part.
Thank you, Roman. Okay, we run out of time, so thank you everybody. The webcast is ending, so within the next 24 hours you will receive an email that will include the recorded session. Please feel free to share this presentation with your colleagues or whoever will benefit from it. And don't forget also that this comes from some of our reports. So we have a report on VCSEL from Nomade and Yole, and coming soon a report for VCSEL for System Plus. So thank you for joining us today. Do not hesitate to contact us if you have additional questions. You can find your appropriate contact at the last page of the presentation. Have a good day. Bye-bye.